Welcome back everyone. In today's video, I'll be explaining AtCoder Beginner Contest 324. I'll explain the problems from D to F. I've provided the correct Python codes in the video description, so please check it out after you've listened to my explanation. Let's get started with problem D. We are given a string S of length n consisting of digits. Considering all the permutations of string S, check if each constructed number is a square number or not. Our task is to count the number of squares obtained from this operation. So if we will attempt to solve it following the problem's flow, first write down all the numbers from permutations, then check if each is square or not. However, we can't do that because the length n is at most 13 and the number of permutations is factorial 13, which is about 10 to the 9th. Now, can't start with the left side set, but how about the right side set? We want to know all the possible square numbers string S can generate, but they can be at most 13 digits and less than 10 to the 14th. Its size is 10 to the 7th and it's small enough. So first we write down all the squares and then check if each square can be generated by S and its permutation or not. Let's think about how to check each square can be generated by S or not. I'll explain it with 48 squared. First, we prepare a list of length 10 named count and define count of I as counts of place value I in 48 squared. Then, fill in the list. Similarly, we define count of S using the original string S. Then, we only need to check if count equals count of S or not to know 48 squared can be generated by S. This doesn't take much time because digits are small enough, so this solves the problem. However, be careful when the digit of a square number is smaller than the digit of string S, like 18 squared. We mustn't use it as 324, but must fill it with leading zeros to n digits. This finishes the explanation of problem D. Let's proceed to problem E. We are given n strings from S1 to Sn and a target string T. We concatenate two strings out of n so that it contains T as a not necessarily contiguous substring. Our goal is to count the number of pairs of two strings Si, Sj satisfying the condition. Of course, we can't check every pair. So let's think about how to paraphrase the condition that Si, Sj contains T as a simple relation. Suppose Si and Sj are given as follows. Si constructs the first part of T, so starting with the first character of Si, we want to know how many characters match between Si and T. In this case, Si can construct the first two characters of T. On the other hand, Sj constructs the last part of T, so starting with the last character of Sj, we check how many characters match between Sj and T. Then we'll find the last two characters of T can be constructed from Sj. Hence, T is completely contained in Si, Sj. But how about this example? In this example, we only get the first character of T from Si and the last character from Sj. So we can't construct the whole of T. Let's make this idea concrete. We define Li as the number of matching characters from left to right between Si and T, and similarly, Ri as the number of matching characters from right to left between Si and T. Then, the condition that SI-SJ contains T can be paraphrased as Li plus Rj is at least the length of T. So the problem is reduced to the number of pairs I and j satisfying this inequality. Here we have a typical technique related to an inequality with two variables. That is, to fix one variable and binary search the other. To do that, first rearrange it with respect to one variable like I. In this case, we decide to fix j. Then, to binary search list L, sort L in ascending order. Next, for each j, we want to find the minimum index I satisfying the inequality. We denote it n. If we compute n, this means that elements of L whose indexes are n or more are large enough to satisfy the inequality. So we add the number of such i's to the answer. But to find the minimum index n, we adapt binary search to list L. In particular, you can write it like this in Python. This ends the explanation of the problem E. Let's proceed to problem F. There is a directed graph with n vertices and m edges. Each edge has two values of beauty and cost. We select a path from 1 to n and calculate the total beauty per the total cost. Our task is to find the maximum value among all the routes from 1 to n. To solve this problem, two main ideas are needed. The first idea, as the example shows, the shape of the graph is quite unique. Every edge is directed from a smaller vertex to a larger vertex, so the vertices are collinear, and also we don't need to think about the way to return. Hence, we want to use DP. This is the first idea. Well, what values should we manage in DP? This is a bit difficult question. Here, I'll show you an intuitive but incorrect choice of value. We want to define dp of I as the maximum value of beauty per cost from v1 to vi, determine its values from 1, and finally reach dp of n, which seems to be the answer. However, we can't do that. Let's see the counterexample. Suppose we've reached vi and we have two routes from v1 to vi. The total beauty and cost of the upper route are different from those of the bottom, but the values of beauty over cost are the same. Then, suppose the path from vi to vj with the beauty of 1, the cost of 100. Then, after addition, the bottom case becomes larger, so in this case, we should adapt the bottom route. However, if we swap the beauty and however, if we swap the beauty and cost of the new path, the opposite will happen. The uppercase becomes larger. So we should adapt the upper path. From this example, you find that you can't decide which route should be kept if there are two intermediate roots with the same fraction value. So we must think about the value of dp again, more carefully. Then here's the second idea. We can reduce the problem to a decision problem with binary search. This is a typical technique when we run into a difficult problem about max or minimum. If we fix x and suppose the answer is at least x, then the condition can be written like this. Then this is equivalent to saying that there exists a path from v1 to vn satisfying this inequality. Then organize it, and we have this simple expression in red ink. So we just need to find a root with the maximal value of the sum of b minus xc and just check if the maximal value is at least 0 or not. Hence, we define dp of I as follows. And in this situation, passing an h is equivalent to just adding b minus xc. So we define the weight of each edge as a value. This time, dp works well because we just manage integers in its values, not fractions. So I'll explain how dp works from the next slide. I'll show you how the transitions will proceed. We initialize dp of I as 0, but the others as negative infinity. We first check the edges starting with v1 and record the maximal values. Then we move on to v2 and update values. We continue this. Then at last we get the maximal value of dp of n. In this example, we have minus 5. We hope the value is at least 0, so this means that x equals 1 is impossible. This indicates that the answer to the problem is much smaller than 1. We must make the value of x smaller and do the same algorithm. But this ends with logarithmic time by binary search. This ends the explanation problem F. With that, I've completed all the explanations. If you have any questions about the problem or any requests for solving other ABC problems, please feel free to comment. Thank you for watching the video.